Okay, so for the last talk for the session, we'll have Prashanth and talk about local algorithms for polynomials.
Thank you. I'll be talking about some joint works with Amireddy, Manasvi Parashar, Shrikant Srinivasan and Madhusudan. So what do I mean by local algorithms? There's a few different algorithms that we look at. These are like testing, decoding, correction, and local correction. In this talk, I'll mostly be focusing on testing and correction, which I'll also define shortly. And also, what do I mean by polynomials? You can think of these just as some like multivariate polynomials over some field. But yeah, which field do we work with, and like what's the bound on degrees for the polynomials? Okay, the degree is just the maximum degree of a monomial with a non-zero coefficient. And also, yeah, what's the input domain? In particular, if the field is infinite, what's the domain over which we evaluate functions? These are all questions we'll answer as we go through the talk. But yeah, so just quickly, local testing is you're given black box access to some function f, and the question you want to answer by making queries to this black box is the following. You want to test whether the black box is in the family curly f or whether it is far from it. So to understand what far is, you need some notion of distance. In this talk, the notion of distance we work with would be this relative Hamming distance. So for two functions with the same domain, it's just the fraction of points in the domain over which the two functions disagree. And being far, you can think of as being some constant relative distance far from all functions p in your family curly f. And yeah, if you are able to do this in Q queries, we say that the family f is Q locally testable. Similarly, local correction, you want to answer the following question. You are guaranteed that your black box is close to some function p in your family f, and you want to compute the value of the polynomial at an arbitrary point in the domain. So you can think of this as, and the goal is to kind of minimize the number of queries you make and also maximize the error up to which you can get this local correction. And you can think of this as kind of going from some average case guarantee to like a worst case guarantee. So saying that fractional distance of f and p is small is like a average case guarantee that your black box computes p, and using this you want to somehow say can actually compute p of any point a with high probability. And so yeah, in some sense local correction is this more general framework of going from average case guarantees to worst case guarantees. There's been several applications of local testing and correction. So most of these applications look at this particular family of functions. So these are degree D polynomials over a vector space. So FQ is a finite field, and you look at all degree D polynomials defined over FQ to the n with codomain FQ. And yeah, this has been very fruitful in different areas in TCS, in particular property testing, complexity theory, and coding theory. And as I mentioned, most of these works consider the domain being this vector space FQ to the n and the codomain being FQ for your functions. But in our work, we look at the following setting. So we look at the codomain or the domain being like a product set. It's like S1 times S2 times Sn, and the codomain being the field f. And yeah, to start with, we can think of all these sets Si to be some arbitrary, like finite subsets of the field. And yeah, maybe in this talk we'll refer to these domains as like grids. Some of our results can extend to this more general setting where each Si can be like a different set, but just for simplicity in this talk, you can think of all the Si's being the same set S. And we'll try to understand this family of functions or low degree polynomials over these domains. And the advantage we have is that now we can also work over infinite fields. But the catch is that the domain now is no longer like closed under linear transformations. So a lot of the techniques that work over the classical setting of fq to the n kind of no longer work, and it's not clear how to get local algorithms in this setting. Also, to motivate it a bit more further, we look at this combinatorial Nullstellensatz. It says that if you have like a polynomial with a non-zero coefficient on a monomial where all the individual degrees are less than the size of s, then it guarantees that there's a point in s to the n over which the polynomial evaluates to a non-zero value. So yeah, this might just look like a simple or just like a purely algebraic fact, but there's been several problems in like graph theory and combinatorics which can be like transformed into questions about polynomials, and this statement can be used to understand like graphs and other combinatorial objects. And maybe of more interest to TCS is this de Mello-Lipton-Schwarzschild lemma, which is also something about polynomials defined over grids. So it says that if you have a non-zero function p over this grid s to the n to f, and it has low degree, then in fact for a random point in your grid it is non-zero with some positive probability, which I denoted by this delta sub st. And yeah, this is also used in a lot of places throughout computer science. I'll refer to this as the size of S as like the arity of the grid. So yeah, in this talk we'll be looking at local algorithms over grids. So yeah, just to as a quick kind of motivation, the idea is that polynomials have good distance over grids, as we saw from the previous slide, and the whole goal of our work is to understand the testability and local correctability of polynomials over grids. And this has been initiated by this work of Kim and Koparthi, where they don't really look at local algorithms, they just want like efficient decoding algorithms over grids. But yeah, the local version of this problem has been considered by Bafna, Srinivas and Sudan, where they give some local testing and correction algorithms. And yeah, some of these only work when the characteristic of the field is small. And these are also over arity 2. And in a joint work with Amik, Parashar, Srinivasan and Sudan, we showed that degree D1, when the degree is 1, you can also get like local correction and local list correction. And in like subsequent works, we kind of extend this to more general domains. So to kind of state our results, think of the set S as a subset of field F, and the arity, which is the size of S, as being some constant. And also think of the degree as a constant. And like I mentioned, we'll look at this family. So curly F is the set of all degree D functions defined over this grid S to the n. And what we show is that you can locally test this family in like a constant number of queries. And going to local correction, we show that you can locally correct in some polylog n queries, where the error is some constant bounded away from 0. And we show kind of stronger things when the arity is 2. So we show that you can actually locally correct up to error approaching like half the distance of the code. So recall that delta st is the relative distance of the underlying code, and we show that as long as the error is less than half the distance, you can actually get local correction. So this is the so-called unique decoding regime. And what happens when the error is like more than half the distance? In this case, we can show that you can actually do this like list correction, which says that you can output like a small list and guarantee that at least one of the functions in your list computes a nearby polynomial. And we can do this up to error approaching like the distance delta st of the code. Yeah. And as like on the maybe slightly orthogonal direction, we look at the case when the characteristic of the field is a constant. So in this case, turns out that you can actually reduce the number of queries from polylog n to a constant number of queries. And you can ask the same question for like larger characteristic, but yeah, the earlier work of Bafna, Srinivas and Sudan show that you actually need like log n queries when the characteristic is 0. But yeah, there's still this gap of polylog n to log n queries in trying to get local correction for polynomials over grids. And just as like a quick summary of some of the consequences of our work, so the local testability question that we considered, in particular when the arity is more than 2, kind of led us to solving some questions about hypercontractivity of certain noise operators. And the local correction algorithms that we described actually imply LCCs over like larger fields like the real numbers. And yeah, we also show some properties of multi-slices. So multi-slice is just like set of points in which all the characters appear like an equal number of times, and studying local correction questions over grids led us to establishing like bounds for low degree polynomials over these special subsets of grids. And we also had to show like certain like symmetric Markov chains over these multi-slices mix fast. And yeah, we also like local list correction is like a stronger version of list decodability, and we get list decodability also over these grids, at least in some regimes. And yeah, we also have a lot of open questions which I might talk with you offline. Thanks.
For a bit late, so we'll take questions.